Dear students, now we will see the Rutherford nuclear model from grade 12 physics chapter 12 atoms. So after this Grigor and Madsen experiment, Rutherford had done an experiment similar to that. That is, this Rutherford has also done this alpha beam scattering experiment. So the diagram shows the experimental setup. So when you look, we have a source of alpha particle, a collimated beam. So it is a collimated beam. So it is a narrow beam of alpha particle which is allowed to strike on a gold foil. This is a gold foil, and see the thickness 10 raised to minus 8 meter thick. So it is a 10 raised to minus 8 meter thick gold foil, and so when this alpha particle strikes this gold foil, either it will pass through the gold foil or it will get deflected or scattered. Either it will get deflected back or it will get scattered at some angle. So in the experimental setup, we have a zinc sulfide screen. This was a zinc sulfide screen. ZNS screen. Okay, so and a microscope was also there. So ZNS screen and microscope. So these were the experimental setup. So we have a source for alpha particle. So this will provide a collimated narrow beam of alpha particle which will strike this gold foil, and this, after striking, most of the particles will pass through or it will get scattered or deflection will happen. And in order to measure the scattering spots or scattering angles, there were a microscope and zinc sulfide screen were there. So, and important thing, the gold foil thickness is 10 raised to minus 8 meter. So we will see a collimated beam of alpha particles of energy 5.5 mega electron volt was allowed to fall on a 2.1 into 10 raised to minus 7, approximately 10 raised to minus 8 meter thick gold foil through a rotatable detector. This ZNS and this microscope together form a detector. Whenever this alpha particles strikes on this ZNS screen, some sparks will be made, and this microscope will measure that particular angle. So this, if the spark is happening here, that means normally the alpha particle is supposed to go like this. If a spark is happening here, means that alpha particle is getting deflected by an angle theta, and by the deflection or by the scattering, it is making a scintillation or a spark over here. So using this microscope and ZNS screen, this detector arrangement, Rutherford was able to measure the scattering angle. Okay, so through a rotatable detector consisting of a ZNS screen and microscope, it was found that alpha particles got scattered. The scattered alpha particles produce scintillations on ZNS screen, and these were counted at different angles. So different scintillations, and how many scintillations. If one scintillation is happening here, means one alpha particle is coming and striking here. If one is coming here, means one alpha particle is coming and striking here. So depending upon the number of scintillation, so he counted the number of scintillation and the angle theta, and he made a plot based on that. Okay, so now let us see that plot. Let us see his observation. So this was his observation. So he took a number of alpha particles got scattered on the y-axis and the angle of scattering on the x-axis, and he observed that as the angle increases, the number of particles is getting less. That means scattering at small angle, means if it is at 20 degree, for example, if it is at 20 degree, the number of particles is more. Number of particles getting scattered at smaller angle is more, and as the angle increases, say 180 till 180, at 180 only very small number of alpha particles is getting scattered. 180 means the rebouncing, only few alpha particles are getting rebouncing at an angle of 180 degree, and at smaller degree scattering is more. That is, number of alpha particles getting scattered at smaller angles, say for 20 degree, the number of alpha particles which is getting scattered is more. So let us see the conclusions or the observations. Most of the alpha particle pass through the gold foil without any appreciable deflection. That was his first observation. And a very small number of alpha particles suffers deflection of nearly 180. As the angle increases, the number of alpha particles getting deflected is becoming less. That is what he observed. Based on this observation, he had made some conclusions. So let us see the conclusion. The scattering of alpha particles is due to Coulomb's interaction between their positive charge and positive charge of the atom. So as I was discussing in the previous model, the alpha particle is positively charged. So if this alpha particle need to be scattered, there should be some positive charge present in the atom. So this scattering is due to the electrostatic interaction or Coulomb's interaction between the alpha particle and the positive charge in the atom. And the second conclusion, an atom has lots of empty space. Why atom is having a lot of empty space? Why? Because most of the alpha particles pass through the gold foil. As we have seen, most of the alpha particles pass through the gold foil. So since the atom is having a lot of free space, the alpha particles are getting passed through the gold foil. So an atom has lots of empty space. And the third point is practically the entire mass of atom is confined to an extremely small central core or nucleus. That's why the deflection is happening. The size of the nucleus, okay, he had approximated the size of the nucleus to be 10 raised to minus 15 meter to 10 raised to minus 14 meter. Then the distance of the electrons from the nucleus is about 10 raised to 4 to 10 raised to 5 times the size of the nucleus. And he also concluded that more the distance, the velocity vector of an alpha particle from the central line of the nucleus, the lesser is the angle of scattering, that is at 20 degree. See, if this is the source, most of the alpha particle will pass through the gold foil. Some are getting deflected. Okay, the number of alpha particle getting deflected at smaller angles is more. As theta increases, deflected alpha particles decreases. Okay, that is, the alpha particle from the central line of the nucleus, the lesser will be the angle of scattering. So that is what it means is, as the distance of the alpha particle from the central line of the nucleus. So if this is an atom and if this is the nucleus, if the alpha particle is coming and striking the central nucleus, then deflecting angle will be more. Then it will get deflected in bigger angles. If the distance of this alpha particle from the center nucleus, as this distance increases, the scattering angle will be less. This is alpha particle, this is positively charged nucleus, so less repulsion. So the scattering angle will be less. Okay, that is what he concluded. The velocity vector, the more the distance of the alpha particle from the central nucleus, the lesser will be the angle of scattering. So these were the conclusions being made by Rutherford, and based on these conclusions, Rutherford suggested a model, or Rutherford suggested atomic model of atom, and he named it to be nuclear model. So normally we will explain it to be as Rutherford nuclear model. So I'll just tell you what Rutherford explained in his Rutherford nuclear model. So in Rutherford nuclear model, he it was based on this alpha particle scattering experiment, and according to this model, what he could have concluded, or what he could have suggested as the model, the entire positive charge or most of the positive charge will be concentrated at the nucleus. So he suggested that most of the positive charge is concentrated at nucleus. Most of the positive charge is concentrated at the nucleus, with electrons revolving around the central nucleus, just like planets revolving around the sun. So the electrons are revolving around the central nucleus, just like planets revolving around the sun. And for any revolution there should be a centripetal force, right? So the centripetal force required for the revolution of electron is provided by the electrostatic force of attraction between this electron and the nucleus. Okay, so there should be, if something is moving in circular orbit, or if something is moving in a circular motion, definitely there will be centripetal force. And as per Rutherford, the centripetal force required for the electrons to revolve around the nucleus is through the electrostatic force of attraction between the central positive nucleus and negatively charged electrons. So we can say, as per Rutherford, the electrostatic force is equal to centripetal force. So due to this, the electrostatic force of attraction will be equal to the centripetal force of rotation. Due to this, the electrons are revolving around the nucleus. And this was the model being suggested by Rutherford, and he named it to be a Rutherford model. So once again, I'm just explaining what was the Rutherford nuclear model. As per Rutherford nuclear model, most of the positive charge of an atom is present in a single place known as nucleus, and the electrons in an atom is revolving around the nucleus in circular orbit, just like planets revolving around the sun. And the force required for this, or the centripetal force, is being or the centripetal force required for this rotation is obtained from the electrostatic force of attraction between the central nucleus and electrons. So this was the Rutherford nuclear model. There were some limitations also for this Rutherford model. We will just see the limitations. So Rutherford model could not explain anything about the stability of an atom, and it could not explain about the electronic structure of atom. He just explained there will be a central positive nucleus and electrons are revolving around, but how these electrons are arranged, things like that are not being explained by this Rutherford. He just said electrons are revolving around the nucleus. That is what he explained. So he cannot say anything about the electronic structure of atom, and he could not explain line spectra. And what is line spectra we will study when we are going through the Bohr model. Bohr model explains about the line spectra of hydrogen. So that also being not explained by Rutherford. So this is all about the Rutherford model of atom. Now we will see two more important topics, that is what is impact parameter and about the distance of closest approach, that we will see. Dear students, we were discussing grade 12 chapter 12 physics, chapter atoms. we were discussing the Rutherford model of atom. Now we will see two important topics. You can expect it to be a 2-mark question, or you can expect it to be as a 1-mark question. So in MCQs also. So first we will see impact parameter. Impact parameter. So impact parameter is nothing but the perpendicular distance of the alpha particles from the central nucleus. So we know in the alpha particle scattering experiment there was a collimated beam of alpha particles. So it is going and striking the atom. See, for example, in the gold foil, if this is the atom in a gold foil and if this is the nucleus and it is a collimated beam, if this alpha particle is going and striking this nucleus, this is the central axis of the nucleus. This is the axis of nucleus. So if this is another alpha particle going, and so the perpendicular distance, the perpendicular distance between the alpha particle and this axis of nucleus, perpendicular distance of alpha particle from nucleus axis is known as impact parameter. So we can say impact parameter is the perpendicular distance of alpha particle from the nucleus axis. So it is the perpendicular distance of alpha particle from the nucleus axis. So that is impact parameter. Now we will see the radius of electron orbit. So as per Rutherford model, there is a central nucleus, positive central nucleus, and these electrons are revolving around the central nucleus. We will see this radius. Okay, so as per Rutherford nuclear model, why this electron is moving in a circular orbit? Because of the centripetal force, and the centripetal force is being due to the electrostatic force of attraction between the electron and the positive nucleus. Okay, now we will see what is the equation for electrostatic force. K q1 q2 by r square. We have seen this one in the first unit, electrostatics. What is 1 by 4 pi epsilon naught q1? First is electron, and the nuclear charges we are taking it to be Zd. The charge of nucleus as Zd divided by r square. And what about the centripetal force? We know it is mv square by r. Since both of them are equal, we can equate them and we can find the value of r. So on equating, we will get 1 by 4 pi epsilon naught Zd by r square is equal to mv square by r. R and r is getting cancelled, and we get r as z e square divided by 4 pi epsilon naught into 1 by mv square. So this is the value of radius of rotation or radius of orbit in which the electron moves. This is the radius of orbit in which the electron moves around the atom. Now let us think about the energy of electron. Okay, so when we are doing this experiment, the alpha particle is coming and striking the atom and it is getting deflected. Okay, so there will be kinetic energy before scattering and once after the scattering. Immediately after scattering or after striking the atom, alpha particle is getting potential energy. So first we will see what is the total kinetic energy, and we will see what is the total potential energy, and we will see the total energy of electron by adding this kinetic energy and potential energy. So first we will see the kinetic energy. So what is equation for kinetic energy? It is half mv square, and v square value we can get it from here, so we will get half m. So v square means is a d square divided by 4 pi epsilon naught m into r. So m and m is getting cancelled, so the kinetic energy will be is a d square divided by 8 pi epsilon naught into r. This is the total kinetic energy. And regarding the potential energy, u, we represent it by u. We know it is k q1 q2 by r. We have studied it in electrostatic chapter itself. So here 1 by 4 pi epsilon naught, q1 is electron, so electrons are negatively charged, so I am taking it as negative minus e. The nucleus is having positive charge Z divided by r. Now this will become minus d square divided by 4 pi epsilon naught r. Now the total energy will be the sum of kinetic energy and potential energy, total energy of electron. So when we add these two, we will get it to be minus d square divided by 8 pi epsilon naught r. That is the total energy of electron. This is the total energy of electron. And here we have a negative sign. The negative sign shows that the electrons are bound to the central nucleus. The central nucleus is positively charged and the electrons are negatively charged. This negative sign of the total energy is it shows that the electrons are bound. This within this electrostatic force of attraction, or it is bound to the central nucleus. That is the meaning of this negative sign. So that's all about the Rutherford model. Now we will see few problems based on this. So let us see one problem. So just see the question. A proton strikes another proton which is at rest. Assume impact parameter is 0, that is head-on collision. Impact parameter, what is impact parameter? It is the perpendicular distance from the nucleus to the nuclear axis to the velocity vector of the alpha particle. So here they are telling like impact parameter is 0, that is it is a head-on collision. How close will the incident proton go to other proton? So a proton is going and striking a proton at rest. So a proton is going and striking a proton at rest. So a proton is positively charged. A positively charged proton is going, it is moving, and it is striking another proton which is at rest. Okay, so this one is having kinetic energy before collision, and after collision what will happen? This kinetic energy will be converted to potential energy after collision. So after collision it will be potential energy, and before collision it will be kinetic energy. So as per energy conservation, we know kinetic energy will be equal to potential energy. So kinetic energy equation is half mv square. Potential energy equation is k q1 q2. Here both are protons, so I am representing it by E and E divided by r as the distance between them. They are asking what is the distance after collision, what will be the distance between them. So I need to find this r. Actually r will be equal to E square k divided by into 2 divided by mb square, or 1 by 4 pi epsilon naught E square 2 E square divided by m v square, or E square by 2 epsilon naught 2 pi epsilon naught mv square. So this will be the radius, or this will be the distance between the protons after the collision. So a proton strikes another proton at rest, head-on collision. How will the incident proton go to other proton? How close will the incident proton go to other proton? So in this question we were finding the value of r.